students. Today we are coming with one question. Let f be a function from w to w, be defined as fn equal to n minus 1 if n is odd, and fn equal to n plus 1 if n is even. Show that f is invertible. Also find the inverse of f. Here w is the set of the whole numbers. So here today we are going to actually discuss the miscellaneous, a few selected question of miscellaneous exercise 1. Okay, this is one of that. So solution to this question will go like this. Let us first write down the question. Okay, it is given to be fn equal to n minus 1 if n is odd, and n plus 1 if n is even. Okay, now let us understand the question here, what the question is telling us. Let us take a few example. F of 0, this domain of the function is whole numbers, so let us start with 0, and f of 0 will be equal to even. It is going to be equal to 0 is even, we are considering it to be even, so f0 equal to 1. F of 1 when it is odd will be going for this definition, n minus 1, so it will become 0. F of 2 will be equal to 1, right? F of 2 will be equal to, n is even, f of 2 will be equal to 3, sorry, f of 2 will be equal to 3. F of 2 is not 1, it will be equal to 3, and f of 3 will be equal to, it will go for the first definition, it will give you 2. Now here we have to notice one thing. F of 0 equal to 1 and f inverse of 0 will be equal to 1. Okay, f of 0 equal to 1 and f inverse of 0 is also equal to 1. F of 2 equal to 3 and f inverse of 2 also will be equal to 3. So if we'll continue like this by taking a few more example, we'll find that the rule of f is same as rule of f inverse. Okay, these are a few examples of that. Okay, but we cannot solve this question like this by giving example, so we have to solve it, we have to prove it, right? So what we'll do for that, we'll take the help of composition of functions. Okay, otherwise also it can be done, but we'll take the help of composition of functions. So what we'll do, we'll try to define one function z, okay, from w to w, which w, this codomain wala w, to w, and this w is the domain wala w, and we'll reverse the definition, right? And let us choose one variable, say m, fm equal to m minus 1 if m is odd, and m plus 1 if m is even. Okay, now let me explain you this also, where from this came. Okay, what we do generally, we'll take m equal to n minus 1. Okay, so here this n is odd. Okay, we find n in terms of m. Okay, now please understand, when this n is odd, this has to be equal to, this m has to be equal to even. So functional definition will be m plus 1, fm equal to m plus 1, where m is even because here n was odd. Okay, this is what we have to understand. If this one has to be odd, this m has to be even, right? Otherwise there is no other choice. If this m becomes odd, then odd plus 1 will become even, but already we have declared that n is odd. Okay, so this is how this came, fm equal to m plus 1 where m is even. And similar case, the other case if we'll take, we'll get fm equal to m minus 1 when m is odd. Okay, so what we'll try to do now, our aim will be, we'll try to find z of f composition, and we'll try to show it to be equal to n, which will be an identity function, and f of z will try to show it to be equal to m if possible, and this is also will become identity function. If these two functions for both the cases become identity function, we can declare that z is the inverse of f. So that is what the aim is. Okay, so let us execute it now. So we'll make two cases, case 1, two cases for z of f, two cases for f of z. So case 1 for z of f. Okay, z case 1, let us make the case first, and n is odd. Okay, so z of f composition is equal to z of, when n is odd, f of n will give us n minus 1. Now we have to understand, here this n is odd, we are considering it to be odd, so n minus 1 will become even, this entire thing will become even. So z of even things become m plus 1, right? So will, this gives rise to n minus 1 plus 1. We need to understand this very clearly. So it will become n. Okay, so we'll make case 2, when n is even. Okay, so let us try to find out z of f in this case. Z of fn is equal to z of fn. Fn when n is even is n plus 1. So we'll write n plus 1. Again, so now we need to understand, n is even, n plus 1 will be odd. So for z, odd will become m minus 1. So it will become n plus 1 minus 1 is equal to n. Okay, now in this case, for both the cases, z of fn becomes n, that is identity function. That is nothing but the identity function. Okay, now we'll go for the two cases for f of z. Okay, case 1, when m is odd. Okay, we'll try to find out f of z now. F of zm, that is f of z of m. Okay, m is odd, so for odd it will go for m minus 1. So f of m minus 1. Okay, now look here, m is odd, m minus 1 will be even. So f when even will become n plus 1. So this gives rise to m minus 1 plus 1 is equal to m. Okay, now for the second case, case 2, when m is odd, sorry, m is even, f of z will become f of z of m. F of z of m when m is even is this m plus 1. So f of m plus 1. Now we need to understand this again. M is even, so m plus 1 will be odd. So f of odd is n minus 1. So m plus 1 minus 1, that is equal to m. So here in this case also, in both the cases, we have got f of zm is equal to m, which is nothing but the identity function. So combining these two cases, c of f is also identity function, f of z is also identity function, we can declare that f inverse is equal to z, and it is defined as, we can choose any one of the two variable. We can either go for m or can be gone for n also. N minus 1, n is odd, okay, and n plus 1 when n is even. and which is nothing but equal to f. So here f and f inverse are equal, as we have seen here in these examples. Okay, so this is how this question need to be solved. So we'll go for the next question. Okay, this is a very nice question actually. This coming up question is, the question is question number 4. This one is, show that of the miscellaneous exercise, if f is running from real number to x such that x belongs to R, x is lying between -1 and 1, defined by fx equal to x by 1 plus modulus of x, is 1 1 and on 2. We have to show it this function to be 1 1 and on 2. Okay, so what we'll do here, the function involves this modulus function, right? So what we'll do, we'll try to bifurcate the domain, that is R, into two half. One is negative, the other one is positive. Okay, we'll make two cases and we'll check for 1 1 and on 2 in for both the cases. Okay, so let us start. We'll make case 1 when x is negative, that is x belonging to minus infinity to 0, 0 is excluded here. Okay, so for showing it to be 1 1, so what we'll do, let x1 x2 belonging to the domain means this subdomain, minus infinity to 0, such that fx1 is equal to fx2. Now we have to see whether x1 equal to x2 or not. Okay, since x1 and x2 are belonging to the negative part, so this functional definition in this case will become fx equal to x upon 1 minus x, because our case is negative, so modulus of x will give us minus of x. Okay, so fx1 will give us x1 upon 1 minus x1 is equal to x2 upon 1 minus x2. Okay, we'll cross multiply to get x1 minus x1 x2 is equal to x2 minus x1 x2. So this x1 x2 and x1 x2 gets cancelled, so we'll be getting exactly x1 equal to x2, and from here we can conclude that f is 1 1 for this case. Okay, so immediately we'll go for case 2. Case 2 will take the other part of the domain, that is 0 to infinity, so that we can cover all the real number. And similarly, in this case also we'll take x1 and x2 to be in this domain, 0 to 0 closed, infinity open, such that fx1 is equal to fx2, and we'll check whether x1 equal to x2 or not. But here the functional definition will now change, so fx in this case will become x by 1 plus x, because modulus of x for positive numbers will give us plus x, right? So clearly this also will give us x1 equal to x2. The calculation I have left for you, so ultimately it gives rise to f is 1 1. So in both the cases the function becomes 1 1, so we'll declare this function to be 1 1. Now we have to check for onto. Okay, for onto also we have to make two cases. Case 1, when x is negative, that is this part, that can be written like this also, x less than, strictly less than 0. So what we do, let y equal to fx. So functional definition in that case is this. Okay, so x by 1 minus x. So what we do, we try to find out x in terms of y. We'll cross multiply to get y minus xy equal to x. We'll try to find out x in terms of y. So x into 1 plus y will be equal to y. So ultimately I'll be getting x equal to y upon 1 plus y, right? Now how to find out the range? We are trying to find out the range actually. This x is negative, so we'll find out the values of y for which the values of y here for which this x is a negative number. So how to do that? We'll take the help of the wavy curve method. Okay, so what are the zeros out here? -1 and 0, -1 and 0, right? So positive here, coefficient positive, and numerator also got positive, so it will start with positive, negative, positive, and we are looking for negative values. X is error negative. So y sign scheme is this. We are and from this we can clearly see that y must lie between -1 and 0. -1 we cannot take, otherwise it will make the denominator undefined. So -1 comma 0. So let me mark this one as a. This is the half of the part of the case 1 range, this one. Okay, half part of the domain. Now we'll check what will happen to the other part of the domain. Okay, so we'll go for the another page. Let me insert another page. Okay, so case 2 is x is greater than equal to 0. Okay, so for this y equal to fx, and functional definition was x upon 1 plus x. Modulus of x will give us plus x. Now again we'll try to find out x in terms of y. Cross multiplication, y plus xy equal to x. So ultimately I'll be getting x equal to y upon 1 minus y. Okay, now we'll try to get the values of y for which x is either positive or 0. Again we'll take the help of what do you call it, wavy curve. Okay, so zeros are 0 and 1. Okay, y coefficient here negative, here positive, so it will start with negative sign, negative, positive, negative. Okay, and we are looking for positive, so y must lie here. So y must belong to 0. Can we take 0? Yes, 0 can be taken. 0 is a value of x. So 0 comma 1 we cannot take, otherwise it will make the denominator 0, which is not possible. So this is the another part of the range. So the range of f will be the union of a and b, which is the union of -1 to 0 open interval union 0 close to 1, which is ultimately equal to -1 to 1 open interval. Now we have to check whether it is equal to the given codomain or not, right? The codomain was this. You see, this is nothing but -1 to 1 open interval. This one is nothing but -1 to 1 open interval. So we have got the range as -1 to 1, which is exactly equal to the given codomain. So this one will prove that f is onto. So this is the solution to the problem. Okay, we'll go for the next question. That's question number 8. Given a non-empty set X, consider Px, which is the set of all subsets of X, where X is a non-empty set, as they say. Define a relation R on Px in Px such that A comma B in Px, A or B, A is related to B on if and only if A is a subset of B. We have been asked whether R is an equivalence relation in Px, and we have to justify the answer. Okay, the solution to this problem will go like this. Okay, question I think you have understood. Two sets A and B are related as long as one is subset of the other. This relation is clearly reflexive, because A set A always can be written as subset of A. So it is reflexive clearly. Now for symmetricity, A related to B will imply A is a subset of B, and B related to A will imply B is a subset of A. Now these two results are not same, okay, unless A and B are equal sets. But A and B cannot be equal sets because they are two different sets in Px, right? So since A or B is not implying B is related to A, therefore R is not symmetric. Okay, not symmetric. implies R cannot be equivalence relation, because we know that for equivalence, for a relation to be equivalence, it has to be reflexive, symmetric, and transitive. So since it is not symmetric, so we can conclude that it is not equivalence. So let us go for the next question. I am taking the next question, question number 10. This is a very important question. Okay, find the number of all onto functions from the set 1 2 3 4 5 6 till n to itself. Okay, so before I solve this question, we need to understand one point here. Okay, so let me take one example. Okay, suppose I'm taking one set containing 1 2 and 3, and one function running from a to a only. So here also 1 2 and 3, and I'm saying that this function is onto. Okay, so onto means every member in the codomain must be connected. Suppose 1 2 I have connected like this. Okay, now if I try to make this function many one, what will happen? If I'll try to make this function many one, suppose now we'll try to make it many one, what will happen? I'll check, we'll see. So 2 is already connected with 1, so 2 can be either connected to this 2 or it can be connected to this 3, right? In both the cases, since it is already connected with 1, if we'll try to connect it to 2 or 3, this function will no longer be a function, because it will violate the definition of the function, right? Similar cases for 1 and 3. So what we have understood, if a function f is running from a set A to itself, and if it is given to be onto, it is readily 1 1, readily 1 1. It is by default 1 1. If it is running from same set to same set, if domain and codomain are same, and if it is declared to be onto, then it has to be 1 1. There is no other option otherwise. Okay, so this is a very important thing to know before we solve this question. So let us go for the solution of this problem. Okay, the solution, now we have to find out the number of onto function. Since the function is running from same set to same set, so it is readily 1 1. So ultimately we'll try to find out the number of onto function in this case, same as number of 1 1 function. Number of 1 1 function is always easier to find than that of onto function. Okay, so we have used this, we'll use this result. Okay, now just draw it. Suppose this is the set 1 2 3 4 is running till n, and is running to 1 2 3, same set. Okay, now we'll try to find out the number of 1 1 function instead of onto, because they are same. Okay, now suppose I wish to find out how many ways I can connect this 1 to any one of these. Since it is 1 1, it can be connected only to one of these elements in the codomain, right? So how many options this 1 will have? Obviously n, can be connected to any one of these n, right? So 1 can be connected with in n ways. Okay, so how many ways I can connect to? Suppose 1 is connected to any one of these. Suppose 2, 1 is connected to 2. So now I cannot connect 2 to this 2, otherwise it will not become 1 1. So how many options for this 2 will remain now? Yes, obviously it will be n minus 1. Similarly for 3, it will be n minus 2, one more, one less, sorry. For this 4, another one less, that is n minus 3, and so on, right? So what will be the number of 1 1 function then? Number of 1 1 function from A to A. And if I call this one to be A, if this given set is A, then the set to set itself will be how many? We have learned these things in what is it called, permutation in class 11. Okay, so fundamental principle of counting, the product of all this, n into n minus 1 into n minus 2 into n minus 3, so on it will go till 3 to 1, right? What is this? This is like well-known expansion. It is nothing but n factorial. And since the function was given to be onto, so the number of, and the set is running from this set to itself, so number of onto function will be same as number of one function. So this will be the answer to this question. Okay, we'll go for the next question. Next question is this.